Hi, boys and girls. The object of this little video is to go over the homework that I posted on Tuesday, which was 20 multiplication and division problems. And you can see on the screen what that looked like. Right? Now, before we get going on this, we ought to maybe just have a little bit of a discussion. When we're taking numbers, in this case, as a science class, our numbers are generated when we take measurements. So let's say in this first problem that we measure the mass of, say, a penny, and the penny comes out to be 0.30 grams. All right, and then I go ahead and I ask you, okay, well, what would the mass of 6 pennies be? Well, you would take these two numbers and you'd multiply them, and you would get some answer in your calculator display. However, we cannot just print out exactly what our calculator tells us. 6 times 0.30 is 1.8. But is that really the proper way to express our answer? Well, that is the question of the day, really. So we're going to have a discussion of arithmetic as it has to do with significant digits. All right, the basic premise here is that the answer to a mathematical problem can be no more accurate than the least accurate piece of data used to compute it. All right, here's an example that might drive this concept home to you a little bit, I hope anyway. Let's just read through this real quick. It says a museum guide explains to visitors that several bones on display are 160,000,005 years old. When questioned about the 5 extra years, the guide replies, 5 years ago, an archaeologist told me that the bones were 160 million years old. Now, is it appropriate to tell the museum visitors that the bones are 160,000,005 years old? Well, of course not, since the 160 million number from the archaeologist was not an exact number. Most dating methods of this type can be off by several million years. The age could easily be 150 million or maybe even 170 million years old. You cannot add the 5 years to the 160 million years in this way, since the accuracy of the bone's age was so low. Right? This is a very extreme example of doing mathematics on measurements. In other words, reporting the accuracy of our conclusion in a way that's appropriate. Okay? Now, as it turns out, when we do arithmetic with significant digits, our rules are broken down into 2 categories. And we're going to deal with the first, which is how we report our answer when we're doing multiplication and division. We'll get to the addition subtraction rules soon enough, but let's just stick with this multiplication and division. All right, the rule here for multiplication and division is that the answer to a multiplication or division problem will have as many sig digs in the answer as that number which had the fewest sig digs that you used to compute it. Now, all of this is given to you in the videos that I had linked to, and I linked to quite a few and put it on Google Classroom. Again, you don't need to limit yourself to just the links I provide you. If you do a Google search for significant digits, multiplication, division, you'll get, I don't know, many thousands of search returns on that. Okay. Anywho, let's go ahead and start taking a look at our homework here. Now, I did post to you a solution sheet here, and I actually included 2 numbers as part of the answer. Right? As you can see here, the first number that I gave to you after each of these calculations was what my calculator tells me Right, if you have a calculator, get it out and just type in 6 times 0.30 and you will get 1.8. But that is not a correct answer. Right? According to the rules for multiplication division, my answer could have only as many sig digs as the number which has the fewest that you use to compute it. Well, we have to go back and take a look at these two numbers, a 6 and a 0.30. How many sig digs are in each of these numbers? Right? Obviously, the 6 here is one significant digit. How about the 0.30? Well, we could go back and do, either the sig dig rules, these 5 rules, or maybe if you're into the Atlantic Pacific rule, put 0.30 here in the middle of the map, and then apply, in this case, the Pacific rule. Since it does have a decimal point present, 0.30 would, when you evaluate it, tells us that we have 2 sig digs. So the 6 is 1 sig dig. The 0.30 is 2 sig digs. So my answer will have only 1 sig dig. So I'm going to have to take the 1.8. I'm going to have to take the 1.8 and I'm sure I'm not going to be able to easily do this. I'm going to round to 1 sig dig. Right? So that means I need to get rid of the number in the 10th spot. Except since it's an 8, it's a number 5 or greater, the 1 gets rounded to a 2, and that's why my answer is 2. All right. Get rid of that. All right, let's try the next one. All right, let's do problem number 2. Okay, we are going to multiply 0.03. Change there. 0.03 by 7 times 210. If we type those 3 things into our calculator, we're going to get the number 44.1. Now, 44.1 has 3 sig digs in it. However, when we go back and check over on the left-hand side of this equation, we find that these numbers over here limit our significant digits to only 1. Right, the 0.03 right here. That's just one. That's supposed to be an arrow. Let me try that again. That guy right there, 0.03. That's 1 sig dig. 1. And how about the number 7? That's also 1 sig dig. Right. And how about the number 210? That's 2 sig digs. Well, we have 1, 1, and 2. What's the lowest number? It's 1. All right, so we need to round our answer to 1 sig dig. All right, that means that we've got to chop this guy right here between the 2 4s here. However, keep in mind that this first 4 is in the tens place. So when we write this out, we got to make sure we throw a 0 at the end. All right. The first number we're cutting off is a number less than 5, which means the 4 doesn't round up. It stays a 4. 44.1 rounds to 40. That is 1 sig dig in the answer, boys and girls. All right. Back up out of this a little bit. Let's take a look at problem number 3. 11.6 times 6.24. Put it into your calculator. 72.384 is your answer. Right. Our answer, though, could only have as many sig digs as the number over here that had the fewest. How many sig digs? 11.6. Well, they're all non-zeros, so they're all significant. There's 3 sig digs. The 1, and the 6. How about the 6.24? Same thing. They're all non-zeros, so that's also 3 sig digs. So our answer will be to 3 sig digs, which means that we're going to keep the 7, the 2, and the 3 and chuck out the 8 and the 4. Right? However, the first digit we're getting rid of, 8, forces the 3 to round up to a 4. So we get 72.4. Let's go out of that. Let's try another one. All right. 0.004 times 5,280. Okay. Put those in your calculator, you get 21.12. Right? How many of these digits should we be reporting in our answer? Well, let's take a look at the left side of the equation. 0.004, how many sig digs? If you answered 1, you got it correct. Right? How about the 5,280 right there? That is 3 sig digs. Which one of those is the smallest? Well, obviously it's the 1 sig dig. So we're going to have to round our answer right here between the 2 and the 1 there. Right? We only want 1 sig dig in our answer. But that 2 is in the tens place, so we can't just write 2. We have to write 20. Written as 20, this only has 1 sig dig. Remember, trailing zeros are not significant when there is no decimal point. Right, we'll get out of that. Let's try number 5. All right. 500.55 divided by 5.11. Put that in your calculator, you get a whole bunch of digits. 2,557.8105. Right? How many of these digits should we be reporting? Well, that depends on how many sig digs are in each of these numbers over here. 500.55, that is 5 sig digs. How about the 5.11? That is 3 sig digs. Which one of those is the smaller number? Well, it's the 3. It's supposed to be 3. All right, so we have to cut this number off after the third significant digit. So we'll let the 2 go, the 5 go, this 5 go, and we're going to have to cut it right there. All right, but the 7 is greater than a 5, so we're going to round up. So it's going to be 256. However, we need to maintain proper place value. This 2 in the original answer is 2,000. So how do we maintain this 2 in the thousands place? We can't just make it 256. We have to throw in a 0. The 0 at the end, the 2 is in the right place value. It's 2,560.